We're going to start with this example now. As soon as there's my pen, I was looking for my pen. Um, this is an algebra 1 example. As you can tell, find the line that goes through those 2 points. This is from elementary algebra. The slope is, y2 minus y1 over x2 minus x1. And then once you have your slope, the equation is going to be of the form y equals mx plus b. And you find your slope first, and then you find the b, substituting either this point or that point, and voila, there we have it. But we're going to use linear algebra, and it may look like we are going to do things in a more difficult way than what we have to, but there's a good reason why we are going to do that. So first, let's use linear algebra to solve this problem from a linear algebra point of view. So if we plug in the 4, if we plug in the -1 for the x, we're going to end up with m times -1. Another way to write that is -1m, because x is the -1, and then the m, we don't know what the m is. I know you can figure that out using basic algebra, but pretend we don't know. We're going to find m and b in one shot instead of finding m first and b using linear algebra. So again, plug in -1 for x, so we end up with -1m. I'm just going to reverse in the order, of course. mx is the same thing as xm. Plus b, we don't know what b is, and the output is going to be 4. I'm just going to put the output on the right side instead of on the left side. Okay, so -1m plus b equals 4. That's from this. And likewise here, we can plug in 2 for x. So 2m plus b, same equation, equals 19. So now we got a system of equations where the unknowns are m and b. And we can put this into a matrix form. So the matrix is -1, 1, 2, 1. Well, that's a nice matrix. Times mb equals 419. And then we can solve this system. It's a matrix times a vector equals another vector. We can draw the augmented matrix corresponding to this system. So -1, 1, 4, 2, 1, 19. So that is the augmented matrix. Some people put a dotted line here to indicate those are the constants. And then we can add 2 of those onto here. So we're going to do R2 plus twice R1. And we're going to end up with -1, 1, 4, 0, 3, 8, and 19 is 27. We can divide R2 by 3. And we have, and independently, but I don't like to do 2 steps in one unless they are independent, and these are going to be independent. We're going to multiply R1 by -1. So we end up with 1, -1, -4, and then 0, 1, 9. And then we can add R2 onto R1. And we end up with 105 and 019. So that means that m, boy, I'm going to try to squeeze that in here. So remember this, it corresponds to m and b. So m equals 5 and b equals 9. And I'm going to go back here and say, well, the answer is, well, after doing this, the answer is y equals 5x plus 9 based on those two numbers, and we can verify quickly if x is -1, -1 times 5 is -5, plus 9 is 4, that checks. 2 times 5 is 10, plus 9 is 19, that checks. So we are guaranteed this is the solution. This is a convoluted way to get the answer. However, it is going to be fruitful when we move on to more points. I was just quickly checking to make sure that I was taping this. All right, so that is example 1. Let's add one more point to that set. Okay, so this is going to be a big example 2. It's going to take us a while to get through this example. So same as example 1, with the additional point, 520. So now we got 3 points. We got -1, 4, 2, 19, 5, 20. So now we have a system of equations just like that with an additional equation. So we're going to have -1m plus b equals 4. I'm copying that from here. That's happened because we plugged in -1 and 4. And then 2m plus b equals 19. 2m plus b equals 19. And then, let me think. Oh, and then we at this point, 5m plus b equals 20. Okay. So the system of equations can be put together as a matrix equation: -1, 1, 2, 1, 5, 1. I'm just going to put the matrix, the augmented matrix, and then we're going to manipulate it to obtain the solutions. So that's corresponding to this column, and then we got the constants 4, 19, and 20. Now I'm going to piggyback on example 1 because this row is the same as this row, -1, 1, 4, -1, 1, 4. This dotted line is a little confusing to me, maybe not to other students, but anyway, -1, 1, 4, 2, 1, 19, 2, 1, 19. So we can do the same manipulations, and we're going to end up with, so we're going to piggyback on example 1 to obtain, of course, the last row is not going to be changed. So we're going to end up with 105, because we're going to do the same row operations. I mean, all these row operations had to do with row 1 and row 2, and those are row 1 and row 2. So the same row operations are going to arrive to the same first 2 rows. 019. The last row, however, will remain as 5120. Okay, and then we can clear the 5 by subtracting 5. So we can do R3 minus 5 times R1. This is much cleaner, so it's easier to manipulate. And we end up with 105, 019. 5 minus 5 is 0. 1 minus 0 is 1. And then 20 minus 25 is -5. Okay, and then we can go farther. If we wanted to, we can subtract from row 3, row 1, or we can leave it like that and realize we end up with a contradiction. but let's subtract. So row 3 minus row 2 will give us 105,019, and then 00 negative 5 minus 9 is negative 14. Okay, so no m's plus no b's, which is not, it's 0, equals negative 14. So this last row says 0 equals negative 14, because remember, those are the constants on the right. This is the augmented matrix, which is a contradiction. Yeah. So we can't find a line that goes through those 3 points. So this is the situation. When we had 2 points, okay, so negative 1, 4 was there, and then somewhere else we had 2, 19, and then somewhere else there is going to be, so when we had this situation, we were able to find the line, this line. Remember, it was 5x plus 9. That line worked beautifully through those 2 points. Perfect. Okay. But we added another point, 520, somewhere around here. And the problem is that this new point, 520, I don't want to be too precise, as far as putting units and everything. But what I do know, what we know now, is that this line doesn't go through this point. That's why we couldn't find the line that goes through the 3 points. And that's a problem. So what we could do is find the closest line to the 3 points. So maybe we're going to miss all 3 points. We're going to compromise, and we're going to find a line that is the closest to that. Instead of this one going through 2 points, if we go through those 2 points, this point and this point, we're going to miss that. We're going to keep those 2 points happy, but that one is not. But then we're going to be too far from that. So what we're going to do is probably move this a little bit. We're going to compromise. Perhaps the line we're going to come up with is going to go through none of the points, but it is going to be the closest to all of them as far as the output goes. That is called the regression line, the least squares regression line. There's many names for it. You have probably done that either in statistics, some algebra, but it turns out that we can do this with linear algebra. In calculus, we do this in calculus 2. I didn't mean 2 as in the number 2. Also in calculus, multivariable calculus is where we typically do it, because we got 2 variables, and we wanted to optimize the distance, the vertical distance among the points and the line, and the variables would be m and b. So that's kind of weird. The variables are going to be m and b, and also in algebra, the variables are going to be m and b, so that we optimize the distance. And the way we're going to go about this problem is going to be by projections, by using the idea of projections. So m and b are going to be, okay, so let's look back at the problem we had in example 2. So we have those 2 matrices, those 2 columns. Let me write it as a matrix problem. So negative 1, 2, 5, 1, 1, 1 multiplied with MB should give us 4, 19, 20, 4, 19, 20, 4, 19, 20. And there is no solution as is. Again, there's no solution. And the reason is this. Okay, those 2 vectors, let's call this vector V1 and this vector V2. And they are in 3 dimensions. So this is what's going on. V1 says this guy, and V2 is this one. And it turns out that this point that we want to achieve by a combination of V1 and V2, so we want to combine so much of this plus so much of that, and we want to end up with this point. But the problem is that this point is outside of this plane. It's not on this plane anymore. That point, let's call it B, is off the plane. So no linear combination is gonna, I mean, we're gonna try to grab this B, but we can't because we are on the plane and this point is off the plane. So pretend, you know, there's a little ant walking on this piece of paper, and I tell the ant, hey, can you reach the tip of this pen? Well, the ant is not gonna, it cannot jump to the, I guess like some ants, I don't know. So assume the ant cannot jump or crawl or anything, cannot get off the paper either. And so, no, it cannot reach that. So, but what we can do, but what the ant can do is that the ant can get as close as the tip as possible. It can get very, very, well, not super close, but as close. If the ant walks away this far, that's far. So the ant wants to go as close as possible to the tip of the, pretend there was sugar that was falling off. So the ant is just going to be waiting right there, you know, right above, right below the pen, the tip of the pen. And that's kind of what's going on here. This is, pretend this is the tip of the pen, and this is kind of the vectors that define the plane underneath, and we cannot reach that. But we can do best, closest. If we project this down, well, yeah, this is kind of at an angle, but if we project down to the plane in a 90-degree angle, we can find a point P, which is the projection. Yeah. We can find the point P that is a combination of those two vectors, and that's better than, even though we don't quite get B precisely, this is a compromise. This is as close as we can get to get B, which is the idea behind here. Okay, we cannot get a line through all 3 points unless you bend the line. I almost break this, but you know, you cannot bend the line to go through the 3 points. We have to compromise, and our compromise will be to find, perhaps to go through none of them, but really close to all of them, as close as possible to all of them. That's kind of what's going on here. This linear combination of those two vectors will not go through B. B is this, which will achieve all 3 points. We can't go through that. We already saw that in example 2. But we can do second best, which is really good. It is desirable still because it is a compromise, and compromises are oftentimes very good. So we get to a compromise. Now, we don't necessarily want P. P is going to be a 3-dimensional vector, which is going to be a combination, a linear combination of those two. We don't want P. P was found in our previous video when we were talking about projections. Remember, we found the what should we call it? The projection matrix. The formula for the projection matrix was, if I'm not mistaken, A transpose A inverse A transpose. Oh, that's not an inverse. That is not a transpose. It's an inverse. I'm looking for my eraser. There it is. I don't know if I run out of eraser. I think. Well, pretend that's not there. And it should be an inverse. There we go. Okay, so we got this formula, and that gave us the projection matrix. Okay, the projection matrix, when multiplied with B, will give us this point. But our problem is not to find that 3-dimensional vector. Our problem is to find the linear combination that gives us this. Okay, so we have to do one fewer step than this, because we don't want the vector itself. We want the linear combination, MB, we don't want the XYZ coordinates of P. We want how much of this guy and how much of this will get to this point. So we are going to stop one step shorter than getting the projection itself. I hope I'm making sense. So the projection is the three-dimensional vector P. We don't want that. We want, so P is really MV1 plus BV2 in this case. So M of that and B of that. Yep. But we don't want the vector. We want M and B. We're after those two numbers. So that means we don't have to do the last A. The equation we really want to solve is this. A, T, A, MB. Now, this MB is not going to be the actual MB that gets us to B, to little O. I just realized I'm using B in two different ways. Watch out. This is the MB as in Y equals MX plus B, the equation of the line. This B corresponds to the vector. Sorry to use the B in two different ways. I just realized that. So this is the vector. And so we have a linear combination MV1 plus B, the scalar B, so that this B, not that B, the scalar B, those are the two unknowns, that this linear combination gives us the projection. And again, we don't want to do that. We want to do one step shorter, which boils down to A transpose A and B equals A transpose B, the vector. So again, sorry to do this. This is the B as in Y equals MX plus B. This is the vector B corresponding to that. Okay. So this is the equation we want to solve. Okay, let's go ahead and do that. Okay, so example 3, same as example 2, which had no solution. Remember, there was no solution. Did we write that down? Yep, there's a contradiction. Remember, 0 equals negative 14. I didn't write a conclusion, which we should. So it is impossible to find a line through all 3 points. So a line through 2 points, no problem. A line through through 3 points, if they line up nicely, no problem. But if they don't line up nicely, as it is the case here, those 3 points are not in a perfect straight line, then it is impossible. So in example 3, we're going to do the same as example 2, except we find the closest line to the 3 given points. Okay. So we have the equation. I'm not going to remember the numbers, so I better check what they are. Oh, yeah. Negative 1, 2, 5 as a column. Negative 1, 2, 5. Then 1, 1, 1, that's the B, times MB times, rather, equals, and I forgot the outputs, 4, 19, and 20. 4, 19, and 20. This one has no solution. However, if we multiply by the transpose on both sides of the equation, that will have a solution, and that solution will correspond to the linear combination of the projection, the linear combination of those two vectors, yep, of the projection. So we're not going to find B. We're changing the problem. We're going to settle for the projection. Some people would not use MB anymore. They would use something else. I'm trying to figure out whether I want to stay with M and B. Let's put a bar on top of it. So because we cannot do this, there's no solution. That was example 2. But can we get a linear combination for the projection? And the answer is absolutely yes. So we're going to multiply on the left with the transpose of this guy. This is A, and this is B. So this is the matrix A, and this is the matrix B. So we are going to have -1, 2, 5 as a row because we're going to do the transpose 1, 1, 1, -1, 1, 2, 1, 5, 1 times MB equals, and then I'm going to try to squeeze that product here, -1, 2, 5, 1, 1, 1 times 4, 19, 20. There we go. So now we have this equation. Now, of course, we're going to multiply those two. So 1 and 4 is 5, and 25 is 30. -1 and 2 is +1, and 5 is 6. -1, 1, 6. 1 and 1 and 1 is 3. Now, the reason why I'm putting a line across is because we're not really solving for M and B as we did earlier. We're going to settle for not the line through the points, but the line that is closest. So we're going to label it something else just to differentiate. Okay. And that is going to be equal to, let's see, -4 plus 38, 34, 134. 4 and 19 is 23, and 20 is 43. Okay. So we want to solve this equation for M bar and B bar. I'm trying to decide how to go about doing this. We can figure out the inverse of this matrix. This matrix has an inverse, and then we can multiply on both sides of the equation by the inverse. Or we can use elimination to figure out M and B. I think we're going to use elimination. So let's write the augmented matrix 36, 134, 6, 3, and 43. Okay, so this is the augmented matrix. It doesn't matter whether I use square brackets or round brackets. I don't know why sometimes I do that, that I change, but I don't care whether you use one or the other or you mix them up as I do. Anyway, but that you have to ask if you go into another class and some instructor is very much into that, then you have to. I think that is a prerogative of the instructor. R1, let's take away 5 times R2 to clear this 30 off with the 6. So we will have 30 minus 30, 0, 6 minus 15, -9. Okay. 6 minus 15, 134 minus, 215. I'm going to do that. So 215 negative and 134 positive. So 5 minus 4 is 1. 11 minus 3, 8. 1 minus 1. So 81. That doesn't seem to. Anyway, let's just keep the 6, 3, and 43. And then we can, yeah, we can get rid of the -9 by multiplying by, so R1 multiplied by -1/9. Yep, so I'm going to continue on the next page here, and we got 0, 1, 9, 6, 3, 43. And then we can clear this off by taking the second row and taking away 3 times the first row, 0, 1, 9. So of course the 6 remains as is, 0. And 43 minus 27, I'm just doing a computation here. Yep, so 13 minus 7 is 6, and 3 minus 2 is 1. Okay, so then we can divide by, so this is just a side computation. We can divide by R2, can be divided by a 6, a number 6. So we end up with 0, 1, 9, 1, 0, 8 over 3. It is 16 over 6, but we can simplify 16 over 6 as 8 over 3. And then we can reverse those two, but we are really looking for M and B. So M, remember M corresponds to the first column, is 8/3. And B equals 9. So the line that is closest to the 3 points is y equals 8/3 x plus 9. Now, there's something I want to figure here. Okay, what is y of -1? If we plug in -1, this doesn't mean y times -1. This means y of -1. It's like a function notation. Well, that is -8/3 plus 9 can be converted into 27/3. So 20, that is 19/3. 19/3. Well, and that is 6 1/3. And the reason why I'm puzzled is because the output of -1 should have been 4. So this is off by a little bit. Let's see, y of 2, and recalling remember the points that we have? The points that were given to us were -1, 4, 2, 19, 5, 20. So that seems a little far away. But let's continue this. So this is 8/3 times 2, which is going to be 16/3 plus 27/3. 16 and 27, 33, 43, 43/3, which is, well, 4 divided by 3 is 1. 13 divided by 3 is 4 and 1/3. 14 and 1/3. It's supposed to be 19. Because remember, the output of 2 is supposed to be 19. We don't get 19, but we are getting a compromise because there's no line that is going to go through all 3 points. So this line is not, I mean, there's no line that will go through all 3. Okay, so I'm going to step ahead. I'm going to jump ahead if you don't mind. 5 times 8 is 40 thirds plus 27/3. That is 67/3. And that is 22. And because 22 would be 66 and 1/3. Did we hit our targets? You know, this is not 4. This is not 19. This is not 20. Oops. We did not hit our targets, but we are as close as we can get of hitting our target using those. I mean, using one line. This is the line that is closest to the points. Now, let me show you what happened here. We are familiar with this calculator. We should be a little bit. Earlier today, I entered these numbers, -1, 4, and then the input here 2, 19, and then the input here is 5, 20. So those are the same inputs and outputs we're using. -1, 4, 2, 19, 5, 20. There they are. Okay. Now the calculator can figure out the closest regression line, number 4, the regression line that is the closest line to all the data we're given. And when I ask the calculator to figure this out, I pressed enter. Notice that we have the slope and the y-intercept. The slope is the same, 2.666, which is the same thing as 8/3. And the y-intercept is 9. So the calculator knows how to do this as well. There's a formula. There is a well-known formula. If you look for formulas, I'm sure you can find the formula for the least or the regression line or the least squares regression. Same thing, the closest line. So we just did it with linear algebra. You can find the formula using calculus. It's a different approach, but you can do it with calculus. Yep. So if we had 4 points, the only thing that it would be different is that instead of having this this 3×2, we would have a 4×2 matrix with a vector here that would be 4. The multiplication would be the same. Eventually, we would end up with a 2×2 matrix, and then we solve the 2×2 matrix, and voila, no problem. Okay. I want to set up a quadratic formula. So if we're given 3 points, in fact, I'm going to use the same 3 points since I'm already they're large, but that's okay. I'm going to use the same 3 points. By the way, I did not use this calculator to solve the problem. The last problem we just did, problem number 3. I just verified that indeed we got the answer correctly using the calculator. So all of these computations were done by hand. Notice I'm multiplying and subtracting by hand. So the expectation is that we're going to use a simple calculator like this one for our computations for the problems that we're given. However, if you use this calculator to check your answer, by all means, go right ahead. I'm sure you can probably find sites on the web. So if you don't have a calculator like this one, you can just ask, how to find the linear regression. And I'm sure there's programs already on the web. I mean, I'm not positive, but I'm pretty sure that's widely known. So there's places where you can probably find the linear regression. But do that to check your answer. Don't do that to find the answer, because the expectation is that we're going to be using linear algebra to do that. Okay. So there's a couple of things I would like to do next. First, let's extend this problem to 3 variables, rather to a quadratic. Okay. Let's see if we want to do that. Okay, so we have 3 points, -1, 4, 219 and 520. Okay, so instead of you finding the line through them, we're going to find, so there's one point, another point, another point. We're going to find the parabola through them. And if you have 3 points, you can always find the parabola through them. So assume you got y, the parabola, equals ax squared plus bx plus c. Okay, we can enter those for x. -1 squared is 1, so 1a. X is -1 still, so negative b minus 1b plus c should be equal to 4. If we enter 2 for x, we're going to end up with 4a plus, again, 2b, or 2b plus c equals 19. If we enter 5 for x, we'll have 25a plus 5b plus c equals 20. So we have a system of equations of 3 unknowns, a, b, c, that correspond to this quadratic function. And we will be able to solve this equation. As long as this is interesting, as long as the points are not on a straight line, the 3 points are not on a straight line, we will be able to solve this equation. Actually, I believe even if they're in a straight line, we will be able to do that. The only thing is that a would be 0, but that would come out of this anyway. So can we solve for a, b, c? And the answer is absolutely yes. Yeah, sure. So I'm not going to do that in the video. I suggest that you do that. And then if you have a graphing calculator, or if you have a computer, you can probably Google how, some site where they have quadratic regression, and then you can verify whether your answer for A, B, and C will correspond to that. Okay, so please finish the problem. Once you find, and by the way, you can verify without even checking with a calculator. What I mean by that, with a graphing calculator or a computer, because if you find A, B, and C correctly, and you plug in -1, 2, and 5, you're going to end up with 4, 19, and 20, respectively. Because there's going to be no compromise. You're going to get 4, 19, and 20 if you find the correct A, B, and C. So we don't even need regression for this problem. You can actually verify. 5. Okay. Same as 4. Same as example 4, with an additional point. So let's say I want to bend this more a little bit. So this was 520. Let's say we go to maybe 1018. So this goes down a little bit. 1018. Whoops. That corresponds to problem 5. Example 5. Yeah. So I didn't want to draw my points again. So those 3 points alone correspond to problem 4. So these 4 points are for problem 4. But if we add one more, now we got 4 points. That is what I'm making up for example 5. So what is the corresponding problem? Let me back up a little bit here to example 4 and write down. Yeah. So I'm going to do this in parallel. In example 4, the matrix equation we have at hand will be, let's see, 1, I'm copying the coefficients from those equations. 1, -1, 1, 4. 4, 2, 1, 19. 4, 2, 1, 19. 25, 5, 1, 20. 25, 5, 1, 20. And there's our, well, this is the augmented matrix. So I already anticipated there was going to be a solution. So I should have probably started with the matrix equation, 1, -1, 1, 4, 2, 1, 25, 5, 1, times A, B, C, corresponding to the quadratic equation, equals 4, 19, 20. And this one will have a solution. I'm quite sure there's going to be a solution. There may be fractions because I just came up with those numbers out of the blue, but that's the worst thing that will happen. There's going to be some fractions involved, some negative numbers, perhaps negative fractions, but that's about it. There shouldn't be, other than the fractions, there shouldn't be any major drama with this problem. This is solvable. And except that we are probably going to make a mistake somewhere along the way, so we have to go back and troubleshoot the mistake and then fix it and so forth. Now, if we add one more point, the equation, the matrix equation will start out the same way: 1, -1, 1, 4, 2, 1, 25, 5, 1. But then we have one more equation corresponding to this additional point, 10. So I didn't finish writing this. The point that we're going to add will be 10, whoops, I meant 10, 18, 10, 18. So that the point that makes the bend more so. See, and the thing is, well, let me write this down. So 10 will correspond to 100 because we're going to do 10 squared times A. So we're going to have 100A plus 10, well, 10B, still plus a single C. Yep. And we're going to multiply this with ABC to obtain 4, 19, 20, 18. Okay, but here's the problem. If we attempt to do this, this is going to be like problem number 2. There's going to be no solution. So check that there's no solution. Okay, so no solution. Okay, and if there's no solution, then we have to compromise. We still want a parabola, but we want the parabola to be as close as possible to the 4 points. We are going to compromise. We're not going to get through all the 4 points. We won't be able to. So we're going to settle for second best. And many times second best is good. It's very, very good because it is impossible to get the best. The best is an ideal. It's a pie in the sky. We cannot get it. So it's okay to get second best if the best is the ideal thing. And there isn't, but there isn't one. So anyway, so what we're going to do is, okay, so pretend this is A. I'm going to label this whole matrix as A. Never mind this. And this is going to be B. Oh, so here we got the same problem I had earlier. This is going to be, I want to stay with B, the vector B. So this is the vector B. Please do not confuse that with the letter or the variable B. Same B, but this is a vector, and that is unfortunate that I'm using the same letter for 2 separate things. I'm sorry about that. But what we have right now is, so translated this into just the symbols, we have A, I'm going to put A, B, C equals vector B. That has no solution. No solution. please verify that there is no solution. So what we're going to do is settle for second best, which is going to be an approximation. So, but you're going to take this matrix, transpose it, multiply by that matrix already. So that's going to give us a square matrix. Let's see, this is 4 by 3. So the transpose is going to be 3 by 3, rather 3 by 4. Multiply with this, we're going to end up with a 3 by 3 matrix. So those two multiplied together will give us a 3 by 3 matrix times A, B, C bar. So we're going to, that means we don't have the same equation. We have a different equation equals the transpose, same transpose of this guy times this same vector B vector. This one will have a solution. So with solution, now that solution will not satisfy this equation, but it will be the closest one we can obtain to satisfying this equation. Why? Because we're going to have a projection, and the projection always gets closest to the plane where we actually want the solution. So this is the problem. Those three vectors generate a space. So that's what's going on. We have three vectors that generate a space, and this space may be three-dimensional. Yeah, so we're going to have a space E in a four-dimensional space, and the point is up here. So let's pretend we have the ant, you know, trying to, which is in a three-dimensional space, but we cannot, no matter how we combine those three, we're not going to get to this spot. We won't be able to do it. But there is a projection, an orthogonal projection. That means 90 degrees, and that will assure us that we're going to be as close as possible. So this is B, the vector B, and this is P, the projection of B onto this space. That's a subspace, by the way, of R4. So all of this is in R4. Okay. But we don't really want P. Because after all, we want A, B, C. We don't want the actual vector. We want the combination of those three vectors that get us that. And that those scalars are going to be A, B, and C. So that's why the equation we have is A transpose A, A, B, C with bars equals A transpose, what was the other guy? B. Yeah. So please solve that equation. Yeah, I rewrote it here. It's the same thing. Set up, you know, you got to multiply. This is the same thing as example 3. You know, first verify that there is no solution, and then go through the motions of example 3, except that this matrix is much bigger, of course, and then figure out A, B, C. Once we finish, you can either use a graphing calculator to get, or use some kind of computer program. What I mean by that, somewhere in the web, there's probably, I'm betting, I don't know for sure, but quadratic approximations, quadratic parabola regressions, quadratic regressions. That's what you want to look for. Quadratic regressions are pretty popular. They're I mean, linear regressions. I mean, yeah. I'll be surprised if you don't find some kind of linear regression or quadratic regression on the web, where you can just punch in the inputs and outputs, and then the calculator or the program will tell you A, B, and C. Yeah. The only thing left that I want to go through is why the formula works. So the question we want to answer is why. And this is derived from this picture. Pretend you got a single vector v1. So this, pretend that's the origin, and then this is v1. And so that generates, all the linear combinations of v1 generates, you know, a straight line in both directions. And this is not necessarily a horizontal line, it can be any line. In fact, it's better if it's not, you know, the horizontal line. And then you got your vector B. Yep. And we want the projection here, P. Now P is going to be on the same space as this line. And this is the projection, which means a 90-degree angle, which causes this point to be the closest on the line to B. Okay, okay. And this vector, so B is this point, you know, this is B. That's B. But this vector from P to B is B minus P. That's this vector. Yep. And the thing is, those two, the dot product of those two should be 0 in order to guarantee the 90-degree angle. And that's how we set it up. That's how we start setting this up. So V1 dotted with B minus P, all of those are vectors. I'm not going to put a hat on the B anymore because I'm trying to just explain the general why. So the dot product has to be 0. That is precisely the definition of orthogonal, and it works. If we distribute, before we distribute, this is a dot product of two vectors that are both horizontal or both vertical. We want to translate that into a matrix multiplication. And the matrix, you know, you always multiply rows with columns in matrices. So one of them has to be transposed. And so we're going to transpose the V1. Yep. And so now we don't have the dot product. We have an actual matrix multiplication. B minus P. Yep. And that is equal to 0. So we can, the rest is a little bit of algebra minus, just almost like basic algebra. I'm just distributing P equal to 0. So the transpose of V1, B is equal to the transpose of V1 times little p. And then I'm missing one quick equation. Oh, yes. What I'm missing is that this P is not necessarily right here on V. They don't coincide. So this P is really V1 times some constant, V1 times a constant. It's a stretch or a shrink of V1. And if it's right on V1, then the constant would be the number 1. But I don't want to say most of the time, but it makes sense that most of the time, the projection, if you have a random point, what are the chances that the random point are going to be right above this guy? And by above, I mean, this could be sideways. So above means against, a 90-degree angle. So this P is really V1 times a constant. So I'm going to revert, I'm going to leave it like that. V1T B equals V1T times VC. Yes. So C is how much this has to be, is the coefficient of the linear combination of V1 that gives us P. So this is the coefficient we want, the linear combination coefficient, C. Now, this idea extends to matrices in a natural way. This is just one vector, but if you have two vectors, things add up exactly in the same way. And that's where this equation comes from. We have, instead of V1, which would be the column corresponding to A, we would have just A instead. So V would correspond to just one column, A corresponds to all of the columns together. So it is exactly the same kind of equation. Let me write it again, but the other way. So this first, we will have V1 transpose V1 C equals V1 transposed B. So this is taking the role of V1 transpose V1 C. It's ABC instead of just C, but that's because we have a matrix, so we have multiple columns, and then the transpose times B is exactly what we have here. So everything cascades or dominoes from the dot product equaling to 0. This vector times this vector, dot product equaling 0. That's where everything comes from. So I just wanted to show you where this came from. Make sure you finish up the two. And if you want one more example, 6. Yeah, example 6, because I show you 4, 5, but I haven't done them. So please do examples 5 and 6, 5, 4 and 5, and one more 6, which will be, what was 4? 4 was a quarter. Okay, so 6, we wanted to make it the same as 3, with additional point. I'm going to add the same point we added. What was it? 10, 18. Whoops. 10, 18. But what I mean by this is you got to find the closest. Find closest. Y equals mx plus b through the points -1, 4, 2, 19, 5, 20, 10, 18. Of course, there's going to be no line, and that's why we say the closest. All right, guys. I think this is a very, very productive video. So we'll stop here.